As a different method of coming up with polynomial curve fits through a set number of points, we have Newton polynomial form. So in this case, this is just pure first order simple interpolation. You notice that you have similar triangles with leg lengths DE, CE, AB, and CB. So the ratios of DE, the vertical leg, to CB, so basically rise over run, is equivalent to the rise over run of triangle ABC. So that's just saying the slope is continuous and it's going to go straight through the same location. Notice whenever you put this in more mathematic notation. So a function is equivalent to a constant plus a slope times deviation away from some known value x1. And then you take that definition seen down here below and solve for f of x. You arrive at the format. F of x equals y1, so that would be the random intercept plus some slope as determined here as a distance away from x1 defined by x minus x1. So this slope, for some of you who've already done some numeric work before, will recognize as the derivative. We've been doing this since junior high algebra. That's rise over run. That's slope of a line. It's very easy to calculate what's going on with a first order curve. But this, little did you know, was first order Newton's polynomial form, where your coefficient initially was the y1 value, and then the slope was given as a2, and that's two coefficients out of the way on your path to very high order curve fits. Now, I describe this method as typically starting very simple. This is an exceptionally simple start to how you define slope and intercept for a straight line. It's going to get complex. It's going to look like each one of these definitions because we're going to continue on to A3, A4, A5, so on and so forth. And their definition will become taxing. Intimidating, maybe, is the right word. It gets easier. There is a shortcut method called a division tree, Newton's polynomial tree, whatever you might want to call it, that simplifies this whole process. So fair warning that it's going to look scary before it gets easier, so just stay until the end and you'll be set. So it's curious now, if we expand this form out, we have a1 plus a2 deviation from x plus a3 deviation of x from x1 and x2 multiplied together. So notice this is now a quadratic form, second order curve. Thus the inflection of the curve here, we still fit perfectly through 3 points and interpolated any given value x. I mean, technically it works within and outside of that bound, but really we know as engineers interpolation is preferred. Extrapolation can be very bad. But anyway, you go through and solve this given having plugged in x1, y1, x2, y2, and x3, y3 one at a time. So notice what happens when you plug in the coefficient x1, y1. So the output would become y1. A1 is unknown. A2 times x1 minus x1 becomes 0. All right, so that's gone. A3 times x1 minus x1, well, we can stop there because it's gone again. Subtract a number from itself, it's 0. That takes the rest of the term with it. So at the point x1, y1, this simplifies down to y1 equals x1. Or excuse me, I should say y1 equals a1. So the first a, which was unknown, follows the exact same format as the first order curve fit. So let's continue on, taking this new knowledge with us. In fact, I'm going to flip over to the surface just so we can keep this a bit tidier. So I'm going to write out the form of equation 651 when plugging in x2, y2. So we can say y2 equals a1. We previously determined that to be y1 plus a2 times x2 minus x1. That's where I've plugged in x2 for the previously unknown value of x, plus a3, x is unknown, so that'd be x2 minus x1. Oops. And then x2 minus x2, which thankfully, there it is. That one goes to 0, and it's gone. So that takes the whole longer term with it. But look, now everything else in the equation is known. It looks like 1/2. That's actually y2. So you can do y2 minus y1 divided by x2 minus x1 equals a2. And all of a sudden you realize that we are right back at the definition for A2 from the linear form. So even though we have done a higher order form, the first two coefficients worked out exactly the same, which is really a massive advantage of this process, because the only thing that is new is the definition A3, which once we solve for, we find is defined here. A3 is the only term where, if you take this preceding knowledge, it doesn't cancel everything out. In fact, just to plug everything in, sure, we'll continue on with the surface writing. Do the base equation once again, so we get y3, take the knowledge we already know, that's y1 equals a1 plus a2 multiplied by x3 minus x1. Actually, a2 has a definition now, so let's give ourselves the room to write that. So it'd be y2 minus y1 divided by x2 minus x1. Take a breath, lots of stuff going on. Let's do now the x3 minus x1. And here's where the new stuff comes in. Finally, we have a3 times x3 minus x1 multiplied by x3 minus x2. Okay, so all you have to do, to make it sound simple, is just solve for A3, move everything around, and then you have your definition, because notice every single other element. Known, known, everything with a subscript, known. I'm not canceling these out to zero, I'm just crossing out the things we know what they are. A3 is the only thing left we need to find. Okay, back to the book. They rearranged it for us. There's the definition of A3. If you are comfortable with numeric derivatives, you notice this follows the derivative form of something very interesting. A's continue to A4, and at this point you're thinking, Dr. Hayes, please stop. This is getting very complex. I don't want to know any higher A's. The next one is frightening. It's probably very big, because now you have essentially the A3 form twice in the numerator divided by some distance away from each in the denominator, and that pattern is exactly what makes everything simple. You can continue on and analyze these forms. You can go up to A5, A6, A whatever you want. But to step in and discuss division trees, divided differences, Newton trees, whatever you might want to call these, is the perfect time to do it. This is a table that saves you much calculation. Given a set of input data points, you write them in column form on the leftmost column, so your pairs of x1, y1, x2, y2, so on and so forth. And then you take divided differences once, twice, third, fourth, fifth, sixth, 50th, however many times you want to go about it, depending on how many data points you have to put a curve through. What's nice is that all of your A coefficients are read straight off the top row. This may not be immediately apparent, but let's skip over to the next page and look at the example. A set of data provided, top of the page. X values, Y values, you know how those work. Write the X in column form, write the Y in column form right next to it. So look at here, the difference in Y2 minus Y1 divided by X2 minus X1. That's slope, negative 47. So that becomes the definition of A2. A1 was just the Y naught term, or I should say the Y1 to get the index correct. What's interesting is that this A3 definition, just a couple pages back, was looking rather troublesome. I mean, that's not bad, but I don't want to do that 20 times. And thankfully, by following this division tree method, you're doing the same math, but not repeating yourself. So if you notice, A3 here is actually the combination of these two differences based on these three sets of data taken over the distance from x equals 4, which corresponds to the third point, and x equals 1, which corresponds to the first. So it's just a way of continuing your mathematics to not rehash and recalculate all the things you've already done. If all you wanted to do was a second order polynomial, you can stop there at A3. If all you want to do is a third order polynomial, you can stop at A4, and you don't have to do anything on these diagonal elements beneath it. But in this case, they're doing A5 because they want a fourth order polynomial fit. So they do have to carry these calculations all the way down. So keep in mind, at each location, it is the y difference over the x difference. In fact, let's go down here for a different example. So y was negative 40 minus a negative 5. There we go. Divided by 5 minus 4. Change in height over change in distance. Negative 35. The next row is where you see the ultimate form of this come in. Let's do the middle one so that way we can give you the answer to something that should be the most confusing. You take the previous height, minus 35, minus a negative 5. So that's what the numerator is. Differences in the y values from the previous step. For x values, you go all the way back to the root, though. You go to the root distance you're covering. So this follows a path. You go from there and look at the maximum expanse you're covering. So between 5 and 2 gives a difference of 3. So you take a numerator value of negative 35 minus a negative 5. So it'll be negative 35 plus 5. So it's minus 30 divided by 3. So negative 10 is the output. So that's the process. You keep continuing those trees down and down, where each component is subject to the entire triangle, the entire like Christmas tree shaped triangle of elements behind it. And you make this tree as large as you need to reach the subscript of A required. So if you needed A6, you'd have to add another data point down here and carry that operation all the way out to get A6. Shouldn't be terribly challenging. It might make you a good test question. But that is a good example and a walkthrough of Newton's interpolating polynomial. Perhaps a little bit easier, perhaps a little bit more difficult to set up than Lagrange polynomials. I'll leave that up to you to figure out in your own practice.